All right, so let's talk a little bit about hypothesis testing and how this relates to statistics. Because again, you really need to remember how you're setting up your experiment. You need to set it up correctly, and then you need to know what hypothesis you are testing when you use a particular statistical analysis and what that data from the statistical analysis is telling you. All right, so there are 5 steps to this. So one, you first have to obviously know what the hypothesis you are testing is, right? And so you need to know that both with regards to the null hypothesis and your regular hypothesis. So we spent quite a bit of time earlier this semester really talking about hypotheses. So hopefully this will be just a brief reminder of that. Then, once you have the hypothesis and you have the data, you have to work out the calculated value of the test statistic. This is the value of the statistic that is for your particular data. Right? Then we have a critical value. Usually the critical value is what you're comparing this to. For example, for a t-test, if we're using our cutoff at 0.05, that's our critical value. Anything below 0.05 is statistically significant. We reject the null. Anything above 0.05, we can't reject the null. That means 0.05 is our critical value. Now, for some of these things, it's just arbitrary. We've done that for our 95% confidence interval. We've set that 0.05 at that. But you have to remember that a 0.049 is really not that much different from 0.051, yet one happens to be above and the other below. For some of these other statistics, we're going to have a different critical value, or there's going to be an actual number we have to compare something to. So once you have your calculated value, you have to compare it to the critical value, just like you have to calculate your p-value using a t-test, and then you compare it to our 0.05 cutoff. Right? And that represents the rule. The rule is basically saying if you're above this, then it's not statistically significant. If you're below this, it is. So when you are comparing those values, what tells you if there is a statistical significance and what tells you if there is not? And that's going to be a little different for each thing as well. And then finally, you have to go back to what does this mean in real terms, right? And this is the part that we're really talking about here in this part of the statistical analyses. All right, so real brief. We know that we have the alternative hypothesis. This is the hypothesis that you would write in your proposal. This is the hypothesis that gives you an explanation of an observation. However, it's the null hypothesis that we're actually testing statistically. That null hypothesis says there's no difference, and it's much easier to determine if the idea that there's no difference is rejected or not. If you're saying there's some difference, that is an almost infinite number of possibilities in some difference. But if there's no difference, there is either no difference or there is. And so the null hypothesis is actually what we're testing statistically. Okay. So if your regular hypothesis is true, then obviously your null hypothesis would be rejected. If your null hypothesis is true, then your regular hypothesis at least is not supported. Even if it's not rejected, it's not supported by these statistics if your null hypothesis cannot be rejected. A few other things to talk about. We have one-tailed test versus two-tailed test. You're going to see this quite a bit. The two-tailed test is almost always what you're going to use. Basically, this means that you can have variation in either direction. Right? And if you have continuous data, if you have interval data that's continuous and quantitative, you're going to have a bell-shaped curve, which means by definition you have differences in either direction. So you're almost always going to use two-tailed. A one-tailed test means your variability can only come in one direction, right? And there's a very few examples where this would be the possibility. One might be if you're testing the statistics of births. You obviously cannot have births below 0. You can't have less than 0 births. So in that case, the variation is only going in one direction, right? However, if you're talking about the average number of births, and saying the average number of births is 3, well, now you're back to two-tailed test because you can have 2 that's less than 3, or you can have 4 that's greater than 3. So again, most of the time you're going to have a two-tailed test. There are very few examples where you know for sure that the variation only goes in one direction. And I'll also state this, when in doubt, use the two-tailed test. It's the more stringent statistical analysis. Right? So unless you're absolutely certain of a one-tailed possibility, you should use a two-tailed test. All right, so let's talk about real quick what happens when you get statistical data, right? We're going to go more into how to do the statistics for a lot of these other things soon, but when you get that data back, what does it mean? This is absolutely critical because if you don't take that number and explain what it means, then really all your work has been for nothing, right? So it's not enough to say I rejected my null hypothesis. You then need to figure out what to do with it. Or it's not enough to even say my null hypothesis is accepted. You still have to figure out what you're going to do with it. So you have to go back to the original hypothesis and decide what that statistical data tells you. Right? So let me talk a little bit more what I mean by this. So, for example, what if you fail to reject your null hypothesis? There we go. All right, so here we have some data, and this is just something where that I found. You don't worry about what it actually is of, but this is looking at the growth of yeast in water versus glucose. And you can see, as you might expect, that glucose is able to grow yeast a little bit more, but we have some variation in our different tests. All right, and so we have this, our average is 5 and 10. So the average growth is 10 over here. I'm not going to worry about units in this particular thing, but we have an average of 10, so our growth is basically double on average when you give the yeast glucose than water, right? But we have standard deviation and so forth. If you do a t-test here, if you're comparing and to see if these groups are indeed different, you see the t-test right now is 0.28. Right? That basically means that I cannot reject my null hypothesis, and I cannot state that this data is statistically significant at this point. Does that mean I say, oh, I give up and okay, glucose must not be a preferential carbon source for yeast? Well, in this case, this just means that there's a 28% chance that this is still random variation. So now I need to decide if it's time to get a new hypothesis, or maybe I just need some more replicates. And you can see here, if I add replicates, and these are the exact same values, so I haven't really changed anything up, but I continue to get similar variation, I continue to get similar averages. The average hasn't changed. If I use all this data, I still have an average of 5 and an average of 10. But you can see here my t-test, as we talked about earlier in this semester, that t-test is going down, because the difference is real and I'm consistently getting the same difference in the values there. If there was really no difference, then I would expect by adding more and more of these values that water would start having some higher numbers and glucose lower numbers. It would average out essentially. But since it's consistent, the t-test is going down, but it's still not significant. But if I did this extra set of replicates and my t-test went from 0.28 to 0.09, I would say, okay, maybe I'm onto something, and maybe I just need to see if it still continues to hold true with a few more replicates. Now, that's what to do if your null hypothesis is not rejected, but you think there's a trend, and you're going to create more replicates and see if it continues to maybe start to show significance. But let's say you did reject the null hypothesis. So here I have a different set of data. So my hypothesis here was that nitrogen is going to help algae growth. And so here I have some growth values. Again, I know units are extremely important, but I'm just trying to make a point here. So when I look at the p-value between these two different groups, I reject the null hypothesis. These two groups are definitely different from each other. But now I have to go back and see what that means with regards to the actual data. So my hypothesis was that nitrogen helps algae grow. By rejecting that null hypothesis, because my p-value is less than 0.05, it means that there was a difference, right? Because my null hypothesis just simply said there's no difference, and this tells me that I only have a 3.8% chance that the difference was random variation. So there is a difference. And if I just leave it at that and then say, oh great, I rejected my whole null hypothesis, therefore my hypothesis that nitrogen helps algae grow must be correct, I'd be absolutely wrong. Because if we go back and look at the data here, yes, nitrogen had effect on algae growth, but did it help it in this case? No. It actually seems to have hurt algae growth. And so I would not then want to take this data and say, yay, let's go add nitrogen if I'm trying to create a lot of algae for biofuels, for example, because this data is not showing me that. When you reject the null hypothesis, you absolutely must go back and look at your data and see if it still supports or does not support your original hypothesis. That is absolutely critical. So in every example, in every exam, and in every research experiment you do, do not just stop at the p-value and say the p-value is 0.038, therefore there's significance. Go back and tell what that means. Therefore, there's a statistically significant difference. But you can see here that that significance was that nitrogen appears to significantly kill algae, not help it. That is hugely important that you go back and state what that means in real life. I'm going to reiterate that because that's absolutely imperative. You cannot just stop at a p-value. Yes, you need to give me the p-value. You need to give the reader the p-value, but you then need to talk about what that means with regards to your data. What does this show you? Is there significance? Is there not significance? And if there is significance, is that significance in the direction that you expected? Or is that significance opposite what you expected? And what does that mean? Should you use nitrogen to help algae grow or not in the end? That's what the experiment was for in the first place, so that's what you have to get back to after the statistics. Alright, so with that in mind, the next part of all of this is really just going to be what type of statistical analysis you use. And this is from our reader, but I'm going to try and narrow this down a little bit. But all of this is for parametric data. Alright, all of these are parametric statistics. Now remember, if you're using parametric statistics to determine if two samples or more samples come from the same or different populations, in other words, are they statistically the same or different? If you're using parametric data for this, you have to test if your data is actually parametric first. So this is why we spent a week really talking about how to test if you're parametric, if your data is parametric. So you really need to do this with your data before you do parametric stats. And on an exam, unless I told you that the data is, you can assume the data is parametric, I would actually expect you to be able to do this and then show me that your data is parametric before you moved on to use the parametric stat. Right? If your data is parametric, then the statistical test you use really depends on what you are trying to do and what your data has. So, t-tests. T-tests are only for if you have two groups and only two groups. So this is when you have a control and a test. You cannot use the t-test if you have a control, dose 1, dose 2, dose 3 of your test, because that's actually 4 groups. Then you would have to use an ANOVA. Alright, so t-tests and the z-test I will teach you, those are only for comparing two groups, no more. Now, if you have two groups, the choice of t-test versus z-test depends on how many replicates you have in each population, in each of those groups. If you have less than 30, you basically have to use the t-test. If you have greater than or equal to 30, you can use a z-test. And a z-test is actually really, really powerful. So if you can, oftentimes you want to use the z-test. But the t-test is a little bit more flexible and usable for both under and greater than 30. The other thing that reason you would choose a t-test over a z-test is if your variance between the two groups is not the same. And I'll talk a little bit more about how to test this in the next videos. But a t-test can be used for equal or unequal variance. A z-test, more powerful, but only useful if you have greater than 30 replicates in each group, and if both of those groups have equal variance. So you have to do an f-test to test for that variance first. And then if you have more than two groups, anytime you have more than two groups, you have to use an ANOVA, and we'll get into that in a bit. Alright, so hopefully this table is going to be very useful for you when you try to figure out which parametric test you should use and under which conditions.